Today we're going to look at a classic number theory probability mixture of a problem, as well as a nice extension of that problem. So we're going to start answering the following question, and that is, if we're given two integers at random, what's the probability that they are relatively prime? In other words, if we're given a and b, those are integers, what's the probability that the GCD of a and b is 1? That's what it means for these things to be relatively prime. So let's start with a little exploration of this problem, and then I think we'll be able to write down this probability pretty easily. So I'd like to maybe start with the following observation, and I think this is pretty straightforward, and that is the probability that a, an integer, is divisible by 2 is, I think we can pretty easily say that that is 1/2. And then, well, that's because half of the integers are even. And then, well, we could push this higher. So what's the probability that a is divisible by 3? So I think we can pretty clearly say that this is 1/3. The probability that a is divisible by 5, I think that's pretty clearly 1/5, because 1/5 of all integers are multiples of 5. And I think from this, it pretty quickly extends to the following statement, and that is the probability that an integer a is divisible by a prime p is 1/p. That's because 1/p of all integers is divisible by p. But now let's extend that to two integers. And now here I'm going to use some shorthand notation. So the probability that p divides a and p divides b. So that's the probability that two integers a and b are both divisible by p. Well, let's observe that these are independent events. So that's simply the probability that p divides a times the probability that p divides b. But then, by our observation, which is just right above, that's going to be 1/p times 1/p. In other words, it's going to be 1/p squared. But now what we really want to look at is the opposite of this probability event happening, or the opposite of this event occurring. And so that would be the probability that p does not divide a, or p does not divide b. So let's observe that that's going to be 1 minus the probability that p divides a and p divides b. In other words, it's going to be 1 minus 1/p squared. But now we need to take a step back and see, well, what does it really mean for the GCD of two integers to be 1? Well, that means they share no prime factors. So if we were to go here and say the probability that the GCD of a and b is 1, so that's going to be the product over all primes of the probability that p does not divide a, or p does not divide b. So that means that no primes divide both of these. But if there is no prime that divides both a and b, then that means that the GCD has to be 1. And of course, we're using the multiplicative property of probabilities here. So we've got the probability that they are not both even times the probability that they are not both multiples of 3 times the probability that they are not both multiples of 5, so on and so forth. So now we can maybe use our observation right above to write this as the probability over all primes p, or sorry, the product over all primes p of p squared minus 1 over p squared, where I just simply found a common denominator and put those two things together. Now that might seem like a nice enough formula, but in fact, we can push a little harder on that product and get this down to something even nicer. So let's do that. So this is where we ended up. The probability that a and b are relatively prime is equal to the product over all primes of p squared minus 1 over p squared. Now I'm going to write this in kind of a goofy way. I'm going to write this as 1 over the product over all primes of p squared over p squared minus 1. So I can definitely do that. I'm essentially just taking the reciprocal twice. But now I can rewrite that as 1 over the product over all primes of 1 over 1 minus 1 over p squared. That's just simply by dividing the numerator and the denominator of the denominator by p squared. But now I want to look carefully at this stuff that I'm putting the purple parentheses around. And let's observe that we can in fact expand this as a geometric series. This is a geometric series where the starting term is 1 and the common ratio is, well, 1 over p squared. So let's see, now we can rewrite this as 1 over the product over all primes of 1 plus 1 over p squared plus 1 over 1 plus p plus 1 over p to the fourth plus 1 over p to the sixth, so on and so forth. So there what I did is I just expanded that as a geometric series. But let's observe that when we multiply that all together, perhaps we could take a little closer look at the first couple of terms of this just to get an idea of why this is about to do what it's going to do. Let's observe that this looks like 1 plus 1 over 2 squared plus 1 over 2 to the fourth, so on and so forth. 1 plus 1 over 3 squared plus 1 over 3 to the fourth, so on and so forth. And that's an infinite product. So let's observe that that's going to give us 1 plus 1 over 2 squared plus 1 over 3 squared plus 1 over 2 to the fourth, which is 1 over 4 squared. And then we'll have a plus 1 over 5 squared, which is going to occur from the next term in that product. And then we'll have plus 1 over 6 squared, which we get from 1 over 2 squared times 1 over 3 squared. So I think we can see that what we're getting here is simply the sum of the reciprocal of all of the squares. So we might as well rewrite this as 1 over the sum, as n goes from 1 to infinity, of 1 over n squared. But of course, that has a well-known value via the Basel problem. In fact, we've solved that problem, or we have evaluated this sum many times on the channel before. This is going to give us 1 over pi squared over 6. In other words, we're going to have 6 over pi squared. So I think that's a beautiful result in its own right, that the probability that two numbers or two integers are relatively prime is this 6 over pi squared. It's get this pi squared inside of it. Okay, so now let's move on to the follow-up question, the extension, and the strategy that we'll be using to solve this question is from this nice paper here on the probability of relative primeness in the Gaussian integers. It's by Sanctus and Reed. And, well, put simply, we're going to say, let's say we're given Gaussian integers, so those are numbers of the form a plus bi, where a and b are integers. We could write this as alpha, beta, and z adjoin I. That's how we would say the Gaussian integers. What's the probability that these Gaussian integers are relatively prime? In other words, what's the probability the GCD of alpha and beta is 1? Okay, so let's see how we'll approach this follow-up question. So in order to start tackling this second question, let's recall what the primes look like in the Gaussian integers. So there are three flavors of primes. You either have plus minus 1, plus minus I. Notice that those are the factors of 2. 2 can be factored as 1 plus I times 1 minus I. And in fact, you'll only really need 1 plus I. And that's because all of the rest of these with the other signs are just either the negative multiple, the ith multiple, or the negative ith multiple of 1 plus I. For instance, 1 minus I is negative I times 1 plus I. And so when we talk about things being divisible by primes that are like this, we only need to talk about them being divisible by 1 plus I. Then our next type of prime is of the form plus minus p, or plus minus I times p, and that's where p is prime and it's congruent to 3 mod 4. So like 3 or 7, or let's see, the next one would be 23, so on and so forth. So let's observe that even though I don't have it written down, similar to what we have up here, we only really need to look at the prime p, because negative p and plus minus ip are going to be simply, multiples of p by something that's invertible. So that's essentially equal to p. And then our last type of prime will be of the form r plus s times I, where r squared plus s squared is a prime, and it's congruent to 1 mod 4. So, for instance, 2 plus I is one of these primes. Notice that 2 squared plus 1 squared is 5. That's a prime that is 1 mod 4. And in fact, 5 factors as 2 plus I times 2 minus I. And if you have a prime that's 1 mod 4, it will factor like, well, r plus si times r minus si. I think that's like hand in hand with this third type of prime. Okay, so now what I'd like to do is look at perhaps when these first two types of primes divide certain Gaussian integers. So let's maybe take this first one first, and that would be the following question. And that is the probability that alpha in z adjoin I is divisible by 1 plus I. So I think we can argue this in the following way. Let's look at a multiple of 1 plus I. So we've got 1 plus I times x plus iy. That'll be, like I said, a multiple of 1 plus I. So multiplying this out, we'll get that this is x minus y plus I times x plus y, keeping in mind that I squared is negative 1. Now, the important thing to notice over here is that the parity of x minus y and x plus y is the same. And so that's a condition which I guess we won't prove this super carefully, that is equivalent to one of these numbers being a multiple of 1 plus I. So the parity of the real part and the imaginary part has to be the same. So let's get that written down. So we've got the probability that 1 plus I divides alpha is equal to the probability that the real part of alpha is equivalent to the imaginary part of alpha modulo 2. So that's just a fancy way of saying that the parity is the same. So we can calculate this as follows. So let's first do this as the probability that the real part of alpha is even. So that's going to be 1/2 times the probability that the imaginary part of alpha is even. So that's going to be another 1/2. And then plus the probability that they are both odd, which is going to be another 1/2 times 1/2. But of course, you multiply those together and then add them all up and you get 1/2. So you get something like this. But now what we can do is extend this to the problem that we're really interested in, and that is the probability that 1 plus I does not divide alpha or 1 plus I does not divide beta. So using a similar strategy to what we did before, we're going to see that that is 1 minus 1 over 2 squared. Because the probability that 1 plus I will divide alpha and beta will be 1/2 times 1/2, and then this is the complement probability here. Okay, so now we've taken care of this first type of prime. Now let's go ahead and look at the second type. Okay, so the extension of this first question led us to what we're really looking for, and that is the probability that 1 plus I does not divide alpha or 1 plus I does not divide beta is 1 minus 1 over 2 squared. Now we're going to move on to the second type of prime, and that is what's the probability that alpha is divisible by p? And then we'll bootstrap that to really what we're looking for at the end. Okay, so let's maybe do this with the following argument. Let's set alpha equal to a plus bi. So I guess we could have done that before with the real part and the imaginary part of alpha, but we didn't. And let's notice that p divides alpha if and only if p divides a and p divides b. So, well, what does that tell us? That tells us that the probability that p divides alpha is going to be equal to the probability that p divides the real part of alpha and the probability that p divides the imaginary part of alpha. But of course, those are distinct events. So that means it's just the product of those two probabilities. But the probability that p divides the real part is 1 over p times the probability that p divides the imaginary part is 1 over p. So that means the probability that p divides this Gaussian integer is 1 over p squared. Of course, that's only if p is one of these primes that's 3 mod 4. So that means that we can put this together and say the probability that p does not divide alpha or p does not divide beta is going to be 1 minus 1 over p to the 4th. It's 1 over p to the 4th because the probability that it divides both will be 1 over p squared times 1 over p squared. And then this is, of course, the complement probability. Okay, so now we've got these two types of primes taken care of. Now let's look at the third type of prime, which is going to take a little bit more work. Now we're going to look at our third type of prime. And we're going to answer this question. What's the probability that a Gaussian integer alpha is divisible by this third type of prime, r plus si, where let's recall that r squared plus s squared is congruent to 1 mod 4 and its prime itself. Now we're going to use this thing called Pick's theorem to get us off the ground, but before we do that, let's maybe talk a little bit about what we're doing here. So the way we want to think about this is as follows. So we'll take a Gaussian integer and we'll observe that that Gaussian integer will live as a multiple of this r plus si. That would be this Gaussian integer right here, z times r plus si, where z is a Gaussian integer. So if it's a multiple of r plus si, you can write it as something times r plus si. So it'll live as that, or it will live in the interior of the square, which is defined by this r plus si, built off of this base point of z. So it might look like this is the origin right here, but this has in fact been shifted so that this point z is like our base point. So you can think about this green square kind of extending in all directions and building this lattice within the Gaussian integer lattice itself. Okay, great. So now I think in order to understand what's going on here, we have to know a couple of things. We have to know how many points are within this square, how many lattice points. In other words, how many Gaussian integers are within this square. Then, well, if we can do that, then we're really on our way to determining this probability. So we're going to use this thing called Pick's theorem, which says that if you've got a simple polygon and an integer lattice, we'll call that p, then a of p, the area of that polygon, is equal to I of p, the number of interior points, plus half of b of p minus 1, where b of p is the number of boundary points. Now, I'd like to observe that we can see that a of p here is simply r squared plus s squared. You can see that a couple of different ways. Maybe the easiest way is by noticing that the complex number in this direction here is r plus si, whereas the complex number in this direction here is I times r plus si. But those are going to have the same length, and then multiplication by I just does a rotation by 90 degrees. So that means here we've got a square. But what's the side length of the square here? Well, it's easy to calculate that it's the square root of r squared plus s squared. But that means that the area of the square is, well, r squared plus s squared. Then we can talk about how many boundary points we have here. And I'm going to claim that there are 4 boundary points. There are 4 obvious boundary points. But in fact, that's all of the boundary points. And that's because this r plus si is a prime number. It's a prime Gaussian integer. But that implies that r and s are relatively prime. So that means that the slope of this, written as a rational number, it'll be like, let's see, s over r, and that is in lowest terms, which means we won't go through any integer coordinates from, well, one of these vertices to the other vertex. But now let's observe that we can put this area and number of boundary points together to determine that the number of interior points is r squared plus s squared minus 1. Now we're ready to calculate our probability. So what's the probability that r plus si divides our number alpha? So we can think about this as 1 over the number of interior points plus 1. Well, and why is that? That's because any Gaussian integer will either be one of these vertices at the lower part of this square, or it will be in the interior of this square. You might say, well, it could be one of these right here, but then we would just look at the square kind of up and to the right of that. Or it could be this vertex right here, but then it would just be the square up and to the left of that. So we really only need to look at this lower vertex here. So that's why we have the interior points plus this lower vertex. But now using the fact that we know I of p over here, this is simply going to be 1 over r squared plus s squared. But now we can get to exactly the probability we want, and that's the probability that r plus si does not divide alpha, or r plus si does not divide beta. So that's going to be 1 minus 1 over r squared plus s squared squared, using similar argument to what we've done for all of the rest of those. Okay, so now let's summarize these calculations, and then we'll be finally ready to calculate our final probability. Thanks for sticking around this long into the video. If you're enjoying the video, make sure and give it a thumbs up, and if you're not yet subscribed, consider subscribing. It really helps out. Okay, so now to finish everything off. We know that the probability that 1 plus I does not divide alpha or beta is equal to 1 minus 1 over 2 squared. We did that calculation before. Then if p is a prime that is 3 mod 4, a regular prime, which is still prime in the Gaussian integers, the probability gives us 1 minus 1 over p to the 4th. Now, if we've got one of these new types of primes that are r plus si, or actually a companion to that, which is argued the same way, which is r minus si. The important thing here is that for each of these, we take s to be bigger than 0. So the probability that alpha or beta is not divisible by one of those is 1 minus 1 over r squared plus s squared squared. And they both are the same probability. But notice that that's going to give us 1 minus 1 over p squared, where p is congruent to 1 mod 4. Because primes of this type have the characteristic that r squared plus s squared is a regular integer prime, which is congruent to 1 mod 4. Okay, so now we're ready to finish this whole thing off. So the probability that the GCD of alpha and beta is 1 is going to be equal to the product of these possibilities. That's because we need no prime to divide both of them. So we'll have 1 minus 1 over 2 squared. And then we'll have the product over all primes, which are 3 modulo 4, of 1 minus 1 over p to the 4th, times the product over primes that are 1 mod 4 of 1 minus 1 over p squared. And then we've got to square that whole thing, because that occurs twice, for the prime r plus si and for the prime r minus si. Okay, now we're going to do the following, and that is observe that we can take this 1 minus 1 over p to the 4th and write it as 1 minus 1 over p squared times 1 plus 1 over p squared. I think that's pretty clear. And then we can regroup these as follows. We can write this as the product over all primes of 1 minus 1 over p squared. We take the 1 minus 1 over 2 squared that's out front. We take the one of these that's congruent to 1 mod 4, and then this one right here that's congruent to 3 mod 4. Put all of those products together and we get the product over all primes. And then after that, we're left over with the product over primes congruent to 1 modulo 4 of 1 minus 1 over p squared. And then the product over primes that are congruent to 3 mod 4 of 1 plus 1 over p squared. Now, we already calculated this object right here. That was as part of our question number 1, and we saw that that was 6 over pi squared. So that means all that's left is to hopefully come up with a nicer value of that stuff that I've underlined in blue. Okay, so let's get to that. Okay, so this is where we ended up, and now we're ready for the last couple of steps. So I'm going to take this, I'll bring the 6 over pi squared down, and there's actually a nice way where I can push these two products together with an alternating sign. So I can rewrite this as 1 minus -1 to the p minus 1 over 2 all over p squared. So let's observe if p is congruent to 1 mod 4, then that gives us a positive 1 in that numerator, which means we have 1 minus 1 over p squared. But if p is 3 mod 4, we get an odd number in this exponent, which turns that into 1 plus 1 over p squared. So that replicates exactly what we have above. But now we can do the same kind of trick that we did before on our first question and write that as 6 over pi squared. And then the product over all primes of the following. 1 minus -1 to the p minus 1 over 2 times p to the -2. And then this is all to the -1 power. So again, that's just from doing some arithmetic like we did before for our very first question. But now I can expand each of those out as geometric series, and well, with the first couple of terms, it's going to look like this. So I'm going to have 1 minus 1 over 3 squared plus 1 over 3 to the 4th minus ... and I'll have 1 plus 1 over 5 squared plus 1 over 5 to the 4th ... and so on and so forth. So again, that's from expanding out as geometric series, keeping in mind that I'm going to pick up an alternating sign whenever p is congruent to 3 mod 4, based off of the fact that we're going to have 1 plus p to the -2 there. Okay, nice. But now what we can see is if we multiply all of this out, we're going to get the following. So we're going to have 6 over pi squared, and then we're going to have the sum as n goes from 0 to infinity of -1 to the n over 2n plus 1 squared. And then, well, that's all like in the denominator. In other words, to the -1 power. So what's happening is that this product will turn into this sum. And we can talk our way through that a little bit. So if our 2n plus 1 is congruent to 1 mod 4, then that means we took an even number of these things that are congruent to 3 mod 4, but that's why we're attached to a plus sign. But if this 2n plus 1 is congruent to 3 mod 4, that means we took an odd number of things that were congruent to 3 mod 4, and then we would have ended up with an overall minus sign. So that's how we get this alternating sum of squares of odd integers. But there's a constant especially defined to be this sum, and it's called Catalan's constant, and we generally use the word or the number g for that. So in the end, putting this all together, we have 6 over pi squared times g, where g is that Catalan's constant. So that would be our final probability, the probability that alpha and beta, which are Gaussian integers, are relatively prime, is this 6 over pi squared times g. And that's a good place to stop.